Hello, I'm the awesome tutor, and today we're going to be looking at waves from the Physics P1 topic. The first thing we need to look at is categorizing waves. The first category are the waves electromagnetic or mechanical. Now, what do these two terms mean? Electromagnetic waves are waves that can transfer energy through a vacuum. So they do not need a medium to transfer energy through. They do not need particles. A mechanical wave is a wave that transfers energy through a medium. A medium is just a substance. So the mechanical waves, they need particles to transfer their energy, which is why mechanical waves, they cannot travel through a vacuum because there are no particles. The second category is the wave transverse or is the wave longitudinal. A transverse wave oscillates perpendicular to the direction of energy transfer. Oscillate just means vibrate. Perpendicular means at right angles to. So here we see an example of a transverse wave. The energy transfer is this way, and the waves, they oscillate up and down at right angles to the direction of energy transfer. So they vibrate perpendicular to it. However, for longitudinal waves, they oscillate parallel the direction of energy transfer. So let's say the energy transfer is this way, straight this way, same as with the transverse wave. The longitudinal wave, say we're talking about sound. If this pen is vibrating up and down, it is pushing and pulling the air particles, transferring its energy through them. Imagine you have a slinky and then you push it back and forth. It will look like this. There will be some compressions and rarefactions, as if you have a spring, as I just said. Compressions and rarefactions. The compressions are when the waves are closer together, and the rarefactions are when they are further apart. And this is how a longitudinal wave oscillates. Now we're going to look at measuring waves. Okay, so let's look at this transverse wave. The point from the center point to the top of the wave or the bottom of the wave, that's what we call the amplitude. And the amplitude is the maximum displacement of the wave. So the distance from the center point to either the peak, this is a peak, or to the trough. So we can also say that this can be the amplitude. Now the distance from wave to wave is the wavelength, how long a wave is. Measuring the wavelength, you have to look from either peak to peak or trough to trough. So this is also the wavelength. Now let's look at here. You have to know what frequency is. Frequency is the number of waves past a point per second. Number of waves past a point per second. And it's measured in hertz. 1 hertz means one wave past a point in 1 second. Let's look back at the diagram. What is one complete wave? This is one complete wave from peak to peak, and this is one complete wave from trough to trough. So basically one wavelength, that's how we measure one wave. This equation is very important. V equals F lambda, where V is the wave speed, usually measured in meters per second, and F is the frequency measured in hertz, and lambda is the wavelength measured in meters usually. And in this equation, do not be surprised if it comes up in your exam and you have to use it to solve a problem. Of course, they will give it to you in the equation sheet, but you have to know how to use it. And for that, we're going to answer some questions. Question 1. The sound waves produced by a keyboard travel at 340 meters per second. A note was played on the keyboard and its frequency was 440 Hertz. Calculate the wavelength of the note. Give your answer to 3 significant figures. Okay, first of all, let's write down the equation. V equals F multiplied by lambda. Do we know the wave speed? Yes, we do. It's 340 meters per second. So 340 meters per second equals. Do we know the frequency? Yes, we do. 440 Hertz. 440 Hertz. Do you know the wavelength? No, because that's what we're trying to calculate. You get 1 mark in your exam for substituting these values into the equation. How do you get your second mark? Well, you rearrange the equation and find the answer. To rearrange the equation, well, we want lambda. So lambda multiplied by 440. How do we get lambda on its own? Divide by 440. So lambda is 340 meters per second divided by 440 Hertz. Remember, this is a calculator exam, so you can use your calculator. 340 divided by 440 gives you 17/22 as a fraction, but as a decimal is 0.77272 blah 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 blah. That's going to give you your second mark. For your third mark, you have to round it to 3 significant figures. 1, 2, 3. Here we go. 0.773. What is the unit? It wants it in meters. Well, you use meters per second, you use Hertz, so it's going to be in meters anyway. 0.773 meters, and there's your answer. Now the second question I have made up by myself. The first question I found in an exam paper, and it's a typical question that they will ask you. The second question, I have made it quite a challenge, so let's look at it. A radio wave is transmitted to a house. The distance from the transmitter, I usually like drawing diagrams to represent things. The distance from a transmitter to the house's receiver is 112 kilometers. The radio waves have a frequency of 3 kilohertz and a wavelength of 2 kilometers. How long will it take for one wave to reach the house? Give your answer to 2 significant figures. So what's it asking for? It's asking for a time. How long? Well, the only equation we can use is V equals F lambda. That's the initial equation, sorry. V is wave speed. How do we calculate wave speed? The equation you should know is speed equals distance over time. We have a distance. We have a speed. No, sorry, we don't have a speed. We have a frequency and we have a wavelength. We need the time. So instead of using V, we can use D over T. So distance over time is equals to frequency multiplied by lambda. We know the distance, substitute in the values, 112 kilometers over time, which we're trying to find out, gives you frequency, what's that? 3 kilohertz, multiplied by the wavelength, which is 2 kilometers. Now look at the answer. It wants you to give it in seconds. And here we have everything in kilometers, kilohertz, and kilometers. We do not want that. Let's convert them. 112 kilometers is what? 112 kilometers is what in meters? You have to convert them. So, you should know that 112 kilometers, to make it from kilometers to meters, you times by 1,000. So it's going to give you 112,000 meters. Over time gives you kilohertz. Kilohertz means just hertz multiplied by 1,000. So 3,000 hertz multiplied by 2,000 meters. Now everything is converted. You can start working things out. You have to rearrange the equation. I'm not going to teach you how to rearrange equations. If you want that, go to a maths video. If you rearrange the equation, you're going to get time is that. Put this into your calculator. Remember your brackets. And you get, 0.1866 blah 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 blah. It wants it to two significant figures, so the answer is 0.19 seconds. Now do not be intimidated by that question, because I have made it specifically hard, and I do not think they will ask you something this hard in the exam. But this is your typical question, question 1. So that you should know how to solve. Next. Okay, so reflection. When we look at reflection, we usually look at the reflection of light. Here we have a plane mirror, and in the exam, they will. It's most likely they will represent it like this. This is how a plane mirror is represented in physics. What is this dotted line you see here? This is the normal line. The normal line is the line which is perpendicular to the plane mirror. What does that mean? It is at right angles to the plane mirror. Let's draw a light ray. Say it's coming from here. When it reaches the plane mirror, what do you think will happen to it? It will be reflected. Let's look at this diagram closely. This ray, we call it the ray of incidence, which is the ray that is first being shone onto the mirror. The ray that is reflected, we call this the ray of reflection. And in the exam, they might ask you about the angle of incidence or the angle of reflection, represented by this and this. How do you measure the angle of incidence and the angle of reflection? Well, it is between the ray and the normal, always between the ray and the normal. And a law of reflection, which you should know, is that the angle of incidence is always equal to the angle of refraction. So this angle is the same as this angle. They are the same. They will always be the same. That is how reflection works. So as you see, reflection is a very simple topic. Okay, so in your exam, they might ask you to complete a diagram to show where an image is formed in reflection. So of course you have your two rays of incidence. You need two of them. One is reflected slightly above and the other slightly below. Of course you draw your normal lines. You have to always draw your normal lines. And then the first thing you should do is reflect them at the same angle. So that looks about there. Ray 1 has been reflected, and then the second ray, that should be reflected as well. Say it's reflected about there. That looks accurate. And of course this angle has to equal this angle. Angle of incidence always equals the angle of refraction. So where is the image formed? This diagram might be the one they give you in your exam. In order to show where the image is formed, you look at the rays that have been reflected and you draw lines from behind the mirror for each of those two reflected rays. And where those two lines meet is where your image is formed. Here is our image, and here was our object. Let me just go through that again. Light rays are being reflected off the object onto the mirror. You need two of them. And for those two, you need two normal lines, one above, one below. After they have been reflected, and you've got the observer here, you have to draw lines going from the reflected rays but behind the mirror to find your image. And that is where these two lines intersect. Now the question is this image real or is it a virtual image? Okay, so what is a real and what is a virtual image? Which they might ask you in your exam. A real image is an image that can be projected onto a screen and is an image where light rays meet. A virtual image is an image that cannot be projected onto a screen and is an image from where light rays appear to come from after the image has been reflected, or after light rays have been reflected or refracted. So which one is this image? Is this image real or is it virtual? This image, I can tell you, is virtual because light rays appear to come from it and it is in a mirror. If an image is in a mirror, it is a virtual image. Next. So, refraction. What is refraction? Refraction is a change in direction of a wave when it changes speed due to a change in medium. Now, what the hell does all that mean? Well, let's look at the diagram and find out. When a light ray is shone onto a glass block, it will be refracted. From air to glass, it's refracted towards the normal. As you can see here, the light is bending towards normal. Refraction is the bending of light. But when the ray goes from glass to air, let's just draw the normal. I am not using a ruler here, but you should in your exam. The light ray instead will be bended away from the normal. So from air to glass, it's towards the normal, and from glass to air, it's away from the normal. Those things you have to know, you have to remember them. They might ask you about it in your exam. So let's look here. Why does the light ray bend towards the normal when it goes from air to glass? Well, the medium is changing from air to glass. The direction is changing, but why? Because it changes speed. When it goes from air to glass, the light slows down. And one side of it slows down faster than the other, so that's why it bends. From glass to air, it speeds up. And so it bends away from the normal. Let's look at diffraction now. So, diffraction. What is diffraction? Diffraction is the spreading of waves when passing through a gap or past an obstacle. And diffraction occurs in all waves and can be easily shown by water waves in a ripple tank. Here I have two examples. The first, here are our waves in a ripple tank. There's usually a vibrating beam here which creates these waves. And here we have our boundaries. And the boundaries create a small gap, as you can see, which the wave passes through. When the wave passes through, you can see that it diffracts. It spreads out. Here, for a second example, the gap created by the boundaries is much bigger. So what do you think, how will you think it will affect the diffraction? Well, the wave will still diffract, but less. So, the bigger the gap, the less diffraction. The smaller the gap, the bigger the diffraction, right? No, that is not correct. The maximum diffraction occurs when the gap width is similar to the wavelength. Wavelength is the key word here. Look at the wavelength of this wave. It is very similar to the gap, to the width of the gap, and so diffraction is there is much more diffraction in here. Whereas for the second example, look at the wavelength. It is not similar to the gap at all, and so it diffracts less. It still diffracts, just not as much. So the amount of diffraction of a wave depends on the gap size compared to the wavelength of the wave. A good example of diffraction is sound. Sound has a wavelength of about 1 meter. And if you have a door open, say this is the wall and the door is open. The width of the door is also about 1 meter, and that is how sound can diffract through this gap into other areas. That's how, if you have a door open, you can hear sound from elsewhere in the area, because sound diffracts due to the similarity between its wavelength and the gap width. Now let's move on to an example that the exam board loves to ask you about. Signal problems. Do not be surprised if this shows up in your exam. Example 1. We have radio waves of a short wavelength that are coming from a terrestrial TV transmitter. Now, a terrestrial TV transmitter means locally, so not satellite TV. Here we have 2 hills. So this house is in a valley. Look at the receiver. Do you think that this house will have a good reception or a bad reception? Well, let's look at the width of the hills. Obviously, it's going to be very, very big. Look at the wavelength of the radio waves. They're very short. Do you think that it's going to diffract enough to reach the house? No. It is going to diffract, just not enough to reach the house. Example 2. Radio waves of a longer wavelength, which are more similar to the gap between the hills, and so they will successfully diffract to the receiver, and this house will have a good reception, even if it is in between a valley. This has been the Awesome Tutor. Bye!